Something just came out of 3i Atlas, and scientists are still trying to wrap their heads around it. Not in a horror movie way, not in some alien invasion way, but in a way that might actually be more mind-bending than either of those tired tropes. When this object, only the third confirmed visitor our solar system has ever received from interstellar space, curved around our sun and began its long retreat back into the emptiness between the stars, it did something nobody on Earth was fully prepared for. It erupted. It let loose a burst of gases and chemical compounds that our instruments had never once picked up from anything passing through our cosmic backyard before. And what poured out of that nucleus, in amounts that left seasoned and researchers just staring silently at their screens, was not simply water vapor and dust. It was a chemical time capsule, a diary frozen in molecules and isotopes for billions of years, sealed shut inside a comet that came from a star system so old it may no longer even exist. It came from a corner of our galaxy so frigid, so far removed from anything familiar, that nothing from that region had ever come this close to humanity before. In a study published in the journal Nature on June 22nd, 2026, built entirely on data captured by the James Webb Space Telescope, just cracked open that diary and told us exactly what was written inside. The answer caught off guard the very scientists who had spent months poring over the numbers. It caught off guard the astronomers who had been tracking this object from the very first night it appeared on a screen, and it is reshaping what we thought we understood about how planets and comets can form in other parts of our galaxy. If you want to know what came pouring out of this interstellar wanderer, what it actually means, and why a comet just passing through has handed us the clearest window yet into a distant, ancient world we will never set foot on, stick around. Because what happened with 3i Atlas is one of the strangest and most extraordinary things planetary science has ever run into. Let's rewind to where this whole story begins, because 3i Atlas showed up completely unannounced, and the way the world responded to it turned into one of the most impressive stretches of coordinated science in the entire history of astronomy. On July 1st, 2025, the Atlas Survey Telescope stationed in Rio Hurtado, Chile, spotted something moving across the sky that didn't belong there. That telescope, part of the Asteroid Terrestrial Impact Last Alert System, a NASA-funded network built mainly to keep watch for anything that might one day threaten Earth, flagged the object automatically. Within hours, astronomers on every continent were pulling up their own instruments to get a look. The orbit told the story almost instantly. This thing wasn't born here. Its path through the solar system was hyperbolic, the kind of trajectory only something moving too fast to ever be captured by our sun's gravity can trace. It was passing through from somewhere else entirely. This made it only the third confirmed interstellar object ever detected sweeping through our solar system, following Oumuamua back in 2017 and Borisov in 2019. Astronomers gave it the designation 3i Atlas. The 3 marks it as the third of its kind. The I stands for interstellar. And within days of that first sighting, essentially every major telescope on the planet, along with several spacecraft already out in the solar system, had been turned toward it. What separated 3i Atlas from its 2 predecessors right from the start was activity. Oumuamua was bizarre and puzzling, but it never showed the clear signature of a comet in the traditional sense. No obvious jets of gas, no visible cloud of material surrounding it. Borisov, on the other hand, was undeniably a comet and behaved more or less like the comets we already knew from our own neighborhood. But 3i Atlas was different from day one. On July 2nd, 2025, just 24 hours after the official discovery, astronomers David Jewett and Jane Liu, observing with the Nordic Optical Telescope, confirmed it was clearly active, wrapped in a diffuse, spreading cloud of material being blown off its surface. It had a coma, it had a tail. Multiple observatories confirmed this within a matter of hours of each other. The comet showed a reddish hue, similar to the coloring seen in D-type asteroids and in Borisov, a shade produced by organic compounds on the surface that have absorbed radiation over unimaginably long stretches of time. And it was already shedding dust at a rate you'd expect from an active comet closing in on our sun. At the moment of discovery, 3i Atlas was already releasing roughly 6 kilograms of fine dust particles every second, along with 60 kilograms of larger particles every second. This was not some quiet chunk of rock drifting silently through our system. This was an actively outgassing visitor, and it was about to tell us things nothing else ever had. The comet's path through the inner solar system turned into one encounter after another, one opportunity after another for scientists to point their instruments at it. It swept past Mars in early October 2025, passing at a distance of roughly 29 million kilometers. The Mars Reconnaissance Orbiter caught sight of it. The MAVEN spacecraft, already stationed at Mars, imaged it as well. Even the Perseverance rover, which had been carefully combing the Martian surface for hints of ancient microbial life, paused its work long enough to turn its Mastcam instrument skyward and photograph an interstellar traveler passing overhead. Think about that for a second. A robot built by humans, sitting on the surface of another planet, took a picture of a comet that came from an entirely different star system. That single image is enough to stop you in your tracks. In October, 3I Atlas reached perihelion, its closest approach to our Sun, dipping inside the orbit of Mercury. Then it began swinging back outward. As it pulled away from the Sun and passed Venus in early November, then swept by Earth in late December at a closest distance of roughly 270 million kilometers, nearly every instrument humanity had available was trained on it. NASA's Parker Solar Probe captured about 10 images of the comet every single day for 18 consecutive days as it flew past. The Europa Clipper, a spacecraft en route to study Jupiter's icy moon Europa, was reprogrammed mid-flight to dedicate 8 straight hours of imaging to the comet. On November 6th, the Psyche spacecraft, originally tasked with studying a strange metal-rich asteroid, interrupted its own mission and turned its cameras toward 3I Atlas for 8 hours. The TESS satellite, normally scanning the sky for planets orbiting distant stars, captured 28 hours of observations of the comet in mid-January 2026. More than a dozen separate NASA missions ended up contributing data. European Space Agency missions, including JUICE, the Jupiter Icy Moons Explorer, and the ExoMars Trace Gas Orbiter, added their own observations to the growing pile. By the time 3I Atlas swept past Jupiter in March 2026, coming within about 53 million kilometers of the giant planet before being nudged ever so slightly onto a new path by Jupiter's enormous gravity, nearly 500 scientific papers had already been written about it. But the single most dramatic chapter of this entire visit happened in late December 2025. As the comet was making its closest pass by Earth, NASA's Sphere-X mission, which had been quietly observing it in infrared, captured something researchers could only describe as the comet erupting. Not exploding in some destructive sense, but erupting, suddenly releasing an enormous quantity of material from deep inside itself in a dramatic burst of outgassing that produced a 40-fold spike in water emissions in a remarkably short window of time. To really understand what happened here, you have to understand how a comet is built. Comets are roughly a third water ice, but that ice sits buried deep inside the nucleus, insulated from the sun's harsh radiation by layers of material sitting above it. When a comet first approaches a star, heat needs time to work its way inward. Picture a frozen dessert with a thick insulating shell on the outside. The interior stays frozen solid long after the outer layer has already begun to soften. It wasn't until roughly 2 months after 3I Atlas had already passed its closest point to the sun, as the comet was already pulling away, that the sun's warmth finally reached that buried reservoir of ice and set off a sudden, dramatic release. And what came pouring out wasn't only water. Mixed into that plume of water vapor was methane, methanol, ethane, formaldehyde, and a whole catalog of other carbon-based molecules, chemistry that had been locked in deep freeze inside this object since before our own solar system had even formed. The X-ray detection that followed turned out to be another historic first. Comets native to our own solar system generate X-rays through something called a charge exchange reaction. As gas streaming off the comet collides with the constant flow of particles pouring outward from the sun, it emits a distinct X-ray signature. But every previous attempt to catch this kind of signal from an interstellar visitor had come up empty. Oumuamua gave nothing. Borisov gave nothing. So when Japan's X-RISM satellite picked up a faint X-ray signature coming from around 3I Atlas in late November 2025, it marked the very first time this phenomenon had ever been observed originating from an object born outside our solar system. At the time of that detection, the gas cloud surrounding the comet's nucleus stretched out to roughly 400,000 kilometers, wider than the average distance separating Earth from the Moon, large enough that you could line up all 8 planets of our solar system side by side and still have room inside it. This detection confirmed that interstellar comets interact with our sun's solar wind in fundamentally the same way comets born in our own system do, and it handed astronomers a brand new technique for studying any future interstellar visitor that happens to swing close enough to the sun. The rotation of 3I Atlas shifted in a way that gave researchers a direct physical read on how all this outgassing was affecting the object. Before its close approach to the sun, the comet was spinning with a rotational period of 16.2 hours, meaning it completed 1 full turn roughly every 16 hours. By December 2025, that number had dropped to 7.1 hours. The comet was now spinning more than twice as fast as before. The reason came down to the jets of material blasting off its surface. As gas and dust erupted from the nucleus in specific directions, the force of that escaping material acted like a set of tiny rocket thrusters, pushing against the comet's spin and gradually winding it up faster and faster. Astronomers tracked the variation in brightness caused by this spin, the comet appearing brighter as its active jets rotated to face Earth and dimmer as they swung away, to measure the rotation with increasing accuracy over time. Then came January 22nd, 2026, a date that produced one of the most precise measurements yet taken of the comet's actual physical size. On that day, 3I Atlas lined up almost perfectly along the line connecting Earth and the Sun within 0.69 degrees of a flawless alignment. With the Sun sitting directly behind it from our vantage point on Earth, the shadows normally cast by the comet's dust particles vanished completely, and the light bouncing off that dust combined constructively, producing a 20% spike in brightness. That surge allowed the Hubble Space Telescope to finally isolate the comet's solid nucleus from the glowing cloud of gas surrounding it. The result was a nucleus with a radius of approximately 1.3 kilometers, smaller than the upper end of earlier estimates, but comfortably within the range of active comets we already know from our own solar system. Not a monster, not some city-sized chunk of rock, just an ordinary-sized comet carrying an absolutely extraordinary chemical signature. The jets visible during that alignment let researchers map the surface of 3I Atlas in more detail than had ever been possible before. Using filters to strip away the uniform glow of the surrounding coma, scientists identified 4 distinct jets firing outward from the nucleus. One larger jet, aimed roughly toward the Sun, had already been spotted earlier and was now pointing almost directly at Earth, and 3 smaller jets positioned about 120 degrees apart from one another. That near-symmetrical spacing of the smaller jets caught people's attention almost immediately. Some corners of the internet jumped straight to the idea that such a regular geometric pattern couldn't possibly be natural, that it had to be some kind of artificial construction. But planetary scientists were quick to point out that regular patterns like this can absolutely emerge naturally, driven by the interaction between a comet's rotation, its internal structure, and how volatile materials are distributed just beneath its surface. Specific pockets of ice, heating up and venting gas in a cycle tied to the comet's spin, can naturally produce jets spaced at regular angular intervals as the object rotates. It looks deliberate from a distance. It isn't. And just to close the loop on that speculation entirely, the SETI Institute and Breakthrough Listen ran a dedicated search for radio signals coming from 3I Atlas using the Allen Telescope Array. They found nothing. 0 technosignatures, no radio emissions of any kind. Just chemistry, pure and natural. Now we get to what the James Webb Space Telescope actually found, because the June 22nd, 2026 paper published in Nature stands as the most detailed and most revealing scientific analysis of 3I Atlas published to date. A team led by Martin Cordner of NASA's Goddard Space Flight Center interrupted Webb's regularly scheduled observation queue to point its near-infrared spectrograph, or NAR-SPEC, at 3I Atlas, just as the comet was beginning its retreat from the inner solar system. NAR-SPEC is built to break down the wavelengths of light that different materials absorb and emit. It can pinpoint specific molecules by their spectral fingerprint, the unique pattern of light each chemical compound produces when illuminated. And what it found inside 3I Atlas stopped researchers in their tracks. The ratio of methane to water inside the comet came in at roughly 11 times higher than anything ever measured in a solar system object before. 11 times higher. No comet native to our system, no matter how strange or unusual its chemistry, comes anywhere close to that number. But even more revealing than the methane was the deuterium content. Deuterium is essentially a heavier cousin of ordinary hydrogen. A normal hydrogen atom has a single proton sitting in its nucleus, while deuterium carries both a proton and a neutron. Water molecules can form using either regular hydrogen or deuterium, and the ratio between the two acts like a chemical fingerprint, quietly recording the temperature of the environment in which that particular water and that particular comet originally formed. Cold environments produce more deuterium. Extremely cold environments, the kind you find out at the frozen outer edges of a planetary system, far removed from the warmth of any star, produce dramatically more deuterium than the warmer, sunlit regions closer to a star. The deuterium to hydrogen ratio measured in 3I Atlas came in at approximately 30 times higher than what we see in comets from our own solar system, and roughly 40 times higher than what's found in Earth's oceans. These aren't just extreme numbers for the sake of being extreme, they're direct evidence of a formation. Environments so cold, so far removed from the warmth of whatever star this comet once orbited, that nothing in our own solar system ever formed under comparable conditions. Researchers at the University of Michigan, publishing a separate study in May 2026, independently confirmed this figure. The ratio was higher than anything ever measured in any object from our solar system. As one of the researchers involved, Teresa Pankeo, put it, this stands as proof that whatever conditions gave rise to our own solar system are not universal across the rest of space. That might sound obvious on the surface, but it needed to actually be demonstrated with hard data, and now it finally has been. Put the extreme deuterium ratio together with age estimates drawn from carbon isotope analysis, and the implication becomes staggering. 3I Atlas appears to have formed in the frigid outer reaches of a planetary system that existed somewhere between 10 and 12 billion years ago. 12 billion years ago, the universe itself was less than 2 billion years old. Our sun did not exist yet. Our own solar system would not begin forming for another 7 billion years after that. And whatever star gave birth to 3I Atlas came into existence when the universe was still young, during a period astronomers call cosmic noon, the peak era of star formation, when new stars were being born across the galaxy at a rate far higher than anything happening today. The star responsible for creating this comet is almost certainly long dead. It lived out its life, moved through its stellar evolution, and either burned out or exploded billions of years before anything living ever existed on Earth. The comet it left behind drifted out into the emptiness between stars and simply kept going. It traveled for billions of years. Based on calculations tracing its trajectory back 10 million years, it passed by 62 other stellar systems along the way. But none of those encounters ever came close enough to meaningfully knock it off course. It just kept moving. Eventually, it reached us. And when our sun's gravity finally caught it and pulled it into a close pass, the heat unlocked chemistry that had been sealed away inside it since the universe was barely out of its infancy. A complementary study using the Very Large Telescope in Chile, led by Shriel Apatam of the University of Edinburgh, analyzed the carbon and nitrogen chemistry of 3I Atlas in the form of cyanide, a simple molecule made of one carbon atom bonded to one nitrogen atom. The ratio of different carbon isotopes found within that cyanide added yet another layer of confirmation to the picture already drawn by the deuterium measurements. The carbon-13 to carbon-12 ratio detected in 3I Atlas's cyanide differed from what we typically see in our own solar system in a way that lines up perfectly with an ancient, extremely cold formation environment. Every single piece of the chemistry keeps pointing in the exact same direction. This object came from somewhere very old, somewhere very cold, and somewhere very far away. Researcher Stephanie Milam of NASA Goddard, a co-author on the web paper, offered a comment that puts the entire scientific significance of this discovery into its widest possible context. She explained that for scientists, uncovering these rare isotopic signatures is fascinating on its own. But the much bigger picture here is what it says about the possibility of prebiotic chemistry existing elsewhere across the galaxy. Prebiotic chemistry refers to the molecules that, under the right conditions, can combine and interact to eventually produce the building blocks of life. 3I Atlas carried methanol, formaldehyde, and a range of other carbon-bearing organic molecules locked inside its ice, compounds that astrochemists consider directly relevant to the origins of biological chemistry. To be absolutely clear, the comet did not carry life. Nobody is suggesting that it did. But it carried exactly the kinds of molecules that, given a world with liquid water and a source of energy, could serve as the starting ingredients for life to eventually take hold. And it carried those ingredients here from a star system that existed 10 to 12 billion years ago, from a region of the galaxy so cold and so ancient that the stars forming there today look nothing like our own sun. The fact that these same basic chemical building blocks appear to show up across that enormous stretch of the galaxy's history, spanning wildly different stellar environments, carries real scientific weight. It suggests that prebiotic chemistry isn't some rare fluke unique to our particular solar system. It may in fact be spread throughout the galaxy in ways we are only just beginning to understand. 3I Atlas swept past Jupiter on March 16, 2026, passing within about 53 million kilometers of the giant planet, close enough for Jupiter's gravity to leave a measurable fingerprint on its trajectory. In practical terms, the deflection was tiny, just a shift of a few meters per second in velocity. But across the slow, patient mathematics of interstellar travel spanning billions of years, even a nudge that small can reshape the arc of a journey almost too long to properly imagine. This was likely the single most significant gravitational encounter 3I Atlas has experienced since it first departed its home star system, and it's also the last meaningful encounter it will ever have with any star along its path. After passing Jupiter, the comet kept moving outward. It now sits beyond Jupiter's orbit, decelerating slightly under the pull of the sun's gravity as it climbs away from the inner solar system, before eventually accelerating again once it breaks free entirely. The instruments capable of tracking it are gradually losing their view, but the data they gathered along the way isn't going anywhere. Astronomers now estimate that at any given moment, our solar system probably has hundreds of interstellar objects quietly passing through it. We simply haven't had the detection technology, until fairly recently, to spot them. With the Vera Rubin Observatory's legacy survey of space and time now running in full operational mode, scientists expect a new interstellar object to be discovered roughly once every 1 to 2 years going forward. The sheer volume of science generated by 3I Atlas, nearly 500 published papers, contributions from more than a dozen spacecraft and missions, and observations gathered from the most powerful space telescopes ever constructed, guarantees that this comet will remain a reference point for understanding interstellar visitors for decades to come. Whatever comes next, 4I, 5I, interstellar objects whose designations don't even exist yet, will inevitably be studied and interpreted through the lens of what 3I Atlas revealed. What came out of 3I Atlas, once the sun's heat finally reached deep enough to touch its buried core and the chemistry sealed inside it for 10 billion years came pouring out into space, was a message from the ancient universe. Not a signal in the way we usually imagine one. Not some deliberate transmission. A chemical message instead, written in isotopes and molecules that our instruments were finally advanced enough to actually read. And the message it carried says something remarkable. The raw ingredients for building worlds, for building comets, for assembling the compounds chemistry needs to begin its long, patient march toward complexity, and maybe eventually toward life, already existed in our galaxy when the universe itself was barely 2 billion years old. Those ingredients existed in cold, dark, distant places that our own sun never once warmed. They survived for 10 billion years in frozen silence, drifting between stars, until they finally arrived here and briefly lit up the instruments of a civilization that, until just months before, had no idea any of it was coming.